This morning it is our pleasure to welcome you here on behalf of the International Space University and the University of South Australia Southern Hemisphere Summer Space Program. We are here to present to you our white paper on space sustainability, Common Horizons.
Before we begin, we'd like to acknowledge the traditional owners of the land, the Kaurna people. We'd also like to pay our respects to their elders, both past and present. Common Horizons has been based on the mission to propose collaborative solutions for the Global South that contribute to the sustainability of Earth and humankind. For us here at ISU, the Global South are all nations that touch and are below the Tropic of Cancer.
So what do we mean by Common Horizons? What is Common Horizons to us? Well, as members of an international community, we look out and we can see a common horizon. Not only is that horizon the physical intersection of Earth and space, but also a symbol of our collective interest in establishing the sustainable use of space. Outer space is a province of all humankind, and for that reason, it is our responsibility to manage this important resource if we are to continue to benefit from it in the future. Though we are divided across nations, cultures and continents, we are here today as representatives of humanity in pursuing a common horizon.
We use satellite technology every day. As you walked in, you would have seen questions on the screens. How did you get here this morning? Did you use a GPS? Have you ever needed to communicate to anyone in a rural community? How do first responders know the best way to coordinate in a disaster? All these activities use satellite technology. In order to continue to use outer space to benefit Earth, we must ensure that space is sustainable. To use the Secure World Foundation's definition, space sustainability is the ability of all humanity to continue to use outer space for peaceful purposes and socio-economic benefit for Earth.
So who are we and why are we here today? We have recommendations to pose to you, and our recommendations focus on policy, awareness and technology. So who are we? Well, we're 37 students from 11 countries around the world. We have different backgrounds. We are students, we are graduates, we are engineers, we are lawyers and we are scientists. We've lived and worked together for 5 weeks and we've learnt about space, its environment and its importance for us here on Earth. We have talked to specialists from every field you can imagine. We've talked to astronauts and we have talked and talked and talked about the importance of space sustainability and why it is so important for us here on Earth and why it is important for Earth's sustainability. We were strangers at the start of this program and now we are like family. We've taught our new friends about our cultures and our countries. We've lived, breathed and even dreamt, with the little sleep that we've had, the 3 I's of International Space University: intercultural, international and interdisciplinary. To start us off today, we're going to be talking to you about space applications for the everyday man. And to do that, we'd like to introduce Jack Yeh from New Zealand. Where's Jack? I don't know where. Oh, this is awkward. Should we just do it ourselves or? Where's Jack? Where's Jack? Oh.
Sorry. I must apologise profusely for my lateness. But please, do allow me to explain myself. The word on the street has it that all the satellite systems are down. And as a result, my flight from Sydney was delayed. The rental car company rejected my MasterCard, and on my way here, the GPS malfunctioned, which has led to me arriving here late. But I must also stress, I have superb driving abilities. So to put that in perspective, my airfare's $200. The rental car, $100. A meal at Mawson Lakes Hotel, $15. And no satellite connections, priceless. So that was just one example of how satellite applications is vital to our daily lives and the role it plays at the heart of modern society. I would now like to introduce you to the role of satellite technology in the various industries vital to the economies of the global south. To start us off, do we have a representative from the construction industry?
Hey there. As a
Hi.
construction worker, I have to use GPS data in combination with maps that are derived from satellite images on daily basis for surveying, planning, and levels on site. Even some of our large excavators use multiple GPS receivers for precision movement.
And to our extreme adventure guide.
That's me. As an adventure guide, I use satellites for a number of activities. For one, we use GPS to help us track wildlife in conjunction with environmental researchers. Also, on fishing trips, we use satellites to help us find the best fishing spots. And we use geographic information systems on our mountain bike tours. They show us planned routes and information of the land along the way.
And do we have a representative from rental car company?
Hey, Scott from London Car Rentals. As part of our car rental service, we are now starting to incorporate GPS into all our vehicles, getting information on our car usage. We also use it for tracking of cars where customers are charged more if they travel outside of defined regions.
And our petrol station attendant.
Yes, we're heavily reliant on satellite technology at our petrol station. All our customer transactions go through the satellite dish on our roof, and without it, we're pretty useless at conducting business.
And finally, to our local farmer.
G'day mates, esteemed blokes and Sheilas, Farmer Chris here. Did you know that we use satellite images for monitoring the health of our crops and predicting and managing the best yields we can get? And bugger me if GPS doesn't steer half the bloody farm equipment these days. And truth, wouldn't you know it, both our TV and internet connections come from telecommunication satellites because we live so darn far out of town.
As you can see, this is but a small taste of what satellite technology does in our daily lives. There are some things money can't buy, but for everything else, there's Scott Fisher.
Thanks, Jack. Now, before I begin, I have a confession to make. I'm not from Adelaide. I'm a Queenslander. Does anyone here feel like joining me and admitting to the fact that we are not from Adelaide, but we are from Queensland? Yes, we have one. Now, I have to ask you, since you've been in Adelaide, and I've been here for so many weeks, the weather here is just terrible. One day it's 45 degrees, the next 18 maximum. It's bipolar, I tell you. And Brisbane weather, normally it's beautiful. It's a perfect place to be. Except sometimes. In December 2010 and January 2011, Queensland suffered a number of severe natural disasters. Cyclone Tasha was a Category 1 tropical cyclone which delivered intense amounts of rain, eventually leading to widespread flooding across the state. Cyclone Yazi was a Category 5 tropical cyclone which destroyed much of northern Queensland. Over the course of these disasters, 2.5 million people were adversely affected directly. $5 billion of damages were caused, and 36 lives were lost. It's a tragedy, no matter which way you look at it. But the thing is, it could have been so much worse. In Australia, we are often referred to as the lucky country. And in this instance, we certainly were lucky. We were lucky that we had the technologies to rely on to help us know that these disasters were coming. There were early warning systems, meteorological satellites which existed, which helped us to prepare. Without meteorological satellites, we would not have known that these storms were coming until they hit us. we would not have been able to prepare. We wouldn't have been able to evacuate thousands of people from the towns which we did. We wouldn't have been able to have emergency services on standby. We wouldn't have been able to sandbank up the rivers and make sure that everyone knew that this was coming. If this had come and caught us unawares, who knows how many more lives would have been lost. It was also important with these cyclones to track them and monitor them and to understand what is happening. Because the thing with floods especially is that they don't happen immediately when the cyclone hits. They happen hours, days after, in downstream regions where there's been rain deluges far upstream. This here shows a satellite map of the rainfall from Cyclone Tasha. By analysing where the rain has fallen and detecting and knowing the geography of the land, we can predict where will likely be flooded next, and hence evacuate the towns and further prepare for what is happening. High detailed satellite imagery is also critical for disaster team coordination. We need to know where the rain has fallen, where is flooded, and where we need to send our teams. There's no point sending a team of 100 armed services to a place which has had minor flooding. But it's critical that they get to places where people are stranded, sitting in roofs and on their roof and on bathtubs. And if we don't know where that is, well, we can't get to them and save them. I mentioned before that Australia is lucky, and whilst there is a significant element of luck in our culture, our use of satellite technology does not come from luck alone. Australia is a member of the International Charter for Space and Major Disasters. This is a charter of a huge number of nations around the world who have agreed to supply satellite imagery and information in the event of major disasters. It's been activated more than 366 times by 100 nations since its inception. It's saved so many lives and prevented so much damage across the entire world, not just Australia. To give you some perspective, Geoscience Australia received 600 images from 20 different nations over the course of these disasters. That's a lot of data. That's a lot of information, and it helped save a lot of lives. Now, satellites used for disaster management are just one application. There are so many others which help us in sustaining our environment, sustaining our society, sustaining our economy. And all of these come together in the next presenter. Advait will now talk to you about urbanisation, which is a deep social issue, a deep environmental issue, and also a deep economic issue.
Thank you, Scott. Good morning, ladies and gents. As Scott mentioned, I'll be talking impact of satellite applications on human life and quality of human life. Cities and urban areas have always been a favorite spot for social, economic, and cultural growth. They have been the face of modern development and a perceived place of better life. In India, in the post-independence era of late 1940s, adoption of mixed economies and rapid industrialization and growth in private sector made cities a very prominent and promising proposition. Cities was where all the jobs were. Cities was where the quality of life was. And this attracted a huge rural population to migrate into these urban areas. For India especially, there are two problems with this. Agriculture is the backbone of Indian economy, and agriculture in India is primarily based in the rural sector. This influx of population in the urban areas led to dwindling numbers of next generation farmers. So who's going to take farming after their fathers? There was literally no one to do that. The second problem with this influx is any city at a given point of time with its given resources can only support so much maximum population. The rapidly increasing urban population puts a lot of pressure on basic amenities and resources. And what you have as a result is that people living in houses which are not accounted for, which are not planned for, and they are not planned, they are not accounted, so you can't provide all the basic amenities you need to live a decent life. Problems of food, sanitation, education, all these problems keep getting acute, and it's a vicious circle that starts, and the situation just keeps on getting bad to worse. The city just can't sustain this population. As a result of all this, what you have in India now is Ferraris driving on streets and people living on the same streets, A chunk of population, a community who migrated to this urban area in search of a better life ended up living a life which no one deserves. No one deserves to live like that. So how does satellite application help in this context? Local governments of the cities and townships are now using data from the Geographical Information Systems, GIS, for effective town planning, effective resource management. The whole mission and the whole idea is to give everyone a fair chance, is to give everyone equal opportunity, and give everyone a shot at better life. There are projects which have been taken up in cities like Sangli and are on ground. They are not just plans on tables of some bureaucrats. I will now show you a video which will talk for itself and demonstrate what I'm saying.
The ocean's not healthy, we're not healthy.
One of the greatest threats to elephants today.
They'll be able to take photographs, videos that are GPS located, immediately upload to Google Earth, and use this as a way to protect the forest.
The population of slum dwellers for Sangli, India is between 10 to 15% of the total city's population. The challenges faced by slum dwellers all across the country is lack of access to basic infrastructure and housing.
आम्हाला इथं बऱ्याच गोष्टीचा त्रास आहे. पाणी वेळेवर नाही आहे. गटार वाहतात.
If you don't know where almost half your city is, how can you even think of inclusive planning or good governance? That got us thinking about starting the creation of a slum directory using Google Earth. We decided that having just information and maps on separate layers was not making it very useful. It was important to connect data with mapping information. And so for us, when Google Earth was launched, it was like an answer to our prayers, because remote sensing images were far more accurate, easy to understand, and they suddenly opened up a whole new world in viewing spatial data. And for the first time, you could see within your city where all the slums were. You could have a very planned, systematic way of dealing with development within the city. The whole idea of using Google Earth was to make it available to the entire city at large. And when we decided to take Google Earth into the slum pockets, it was really an empowering experience for all of us. Over the last few years, our experience has been that people resist moving. But when we showed them on the Google Earth that this is where they were, and this is where they would be moving, where they could still have access to their present livelihood means, then they started thinking, oh, maybe this is not such a bad idea.
कसं जे पुनर्वसन होईल ते लोकांना कसं करतात, कचरा टाकल्यावर ते गावाच्या बाहेर आणि जरा गावाच्या बाहेर टाकतात. त्याच्यामुळे आता आम्ही शहरात येतोय, जास्तच आम्हाला आनंद वाटते ह्याच्यामध्ये. आमचा गाडी खर्चाचा पैसा थोडाफार वाचेल. तोच पैसा आमच्या घरात संसाराच्या कुटुंबासाठी खर्चता येईल. आणि महत्त्वाचं म्हणजे सगळे जवळ असल्यामुळे मुलांनाही माझा त्रास होणार नाही. शहरात येतोय म्हणून आमच्या मुलांचं शिक्षणामध्ये बदल होणार, चांगलं शिक्षण त्यांना मिळणार आणि पुढची जी पिढी आहे त्यांच्या नशिबात चांगलं त्यांचं भविष्य उघडणार.
The dream that I share with this organization is to try and give the most vulnerable in our cities a much better quality of life.
आणि स्वतःचं घर होणार आहे म्हटल्यावर माझं सगळ्यात मोठं स्वप्न पूर्ण होतं असं मला वाटतं.
So as you can see, as you can see in this video, that these projects are actually happening on ground and are changing lives. They are touching people. But this is just one part of a bigger solution. It's a curative measure, if you will. It's a curative measure taken after the system has sickened already. What do you do to prevent all this? In our opinion, we think that a bigger solution is required, wherein we have a model which has population spread throughout evenly, and you have an effective network of resources and facilities, so that everyone around the country, the planet, is a part of the greater change, the greater progress. Everyone moves along together. And this cohesion and linkage brings me to talk about telereach. Telereach is defined as technologies and applications which allow remote presence, participation, interaction, and control. Newsflash to all of you. Africa has 11% of the world's population, but has 24% of world's diseases. 2/3 of the world's illiterate adults are just found in the global south. Doctors in India prefer not to serve in the rural parts just because they have a better life in the urban areas. The Millennium Development Model of the United Nations has a plan, has an aim of having quality education and reliable health networks throughout the planet. And telereach is a very important and a key tool in this process. The projects like Pan-Africa e-Network are great examples of how telereach is touching millions of lives. Millions of lives which otherwise were deprived of the blessings of modern technology. They were out of the context and they were nowhere to be seen. The Pan-Africa e-Network currently links 149 sites to educational centers, universities, hospitals, around regional and metropolitan areas across India and Africa. So you can see how satellite application just brings together everyone, makes everyone part of the bigger process, and takes everyone along. Satellite application, remote sensing, telereach, and many others are also used for many other purposes like agriculture monitoring, enhancing mining using robotics, which is done very actively in Australia. It's also used for monitoring climate change. And to talk more about all these things, I'll just pass it on to my friend James.
$8.3 billion people. That is the estimated global population in the year 2030. This massive increase in population is going to need more food and more water. Satellites allow for more efficient farming practices to ensure that we can provide this. Earth observation satellites provide farmers with information about crop health, crop density, crop stress. They can identify problems with their farm before they happen. Position navigation and timing systems can be used in conjunction with this for precision agriculture. A farmer can identify which sections of his farm need how much fertilizer, and he can use position navigation and timing systems to tell him where he is in his field so that the fertilizer can be applied. It's efficient practices like this that will save money, increase production, and provide us with food to sustain this increased population. Groundwater supplies can also be monitored using satellites. The NASA GRACE system monitors the Earth's gravitational field, and it can detect changes in groundwater. Thermal imaging cameras can also be used by satellites. They identify surface cooling, which can indicate groundwater underneath the surface of the Earth. Information about groundwater supplies can be provided to local authorities. so they can take correct decisions on how to use this resource. In direct parallel with this increasing population is climate change. Climate change is the defining issue of our era, and it poses long-term challenges to economic growth. Satellites can contribute to the measurement of the essential climate variables. This is a set of 50 geophysical variable types that directly correlate to the Earth's climate, and satellites make significant contributions to 25 of these. Things like carbon dioxide density, ocean temperature, and sea ice melting. If scientists understand what is going on and they can take a global view provided by satellites, they can better mitigate the effects of climate change, they can understand what's causing climate change, and they can understand the effects of climate change. Satellites also play an important role in raising public awareness. I'm sure by now you've all seen the picture behind me. The picture on the left is from 1999. The picture on the right is from 2010. And they were produced by NASA satellites orbiting the poles. They identify a gradual decrease in Arctic ice over this 11-year period, and they've identified a decrease since the late 70s. It's pictures like this that raise public awareness about the issues of climate change. Satellites allow us to see the big picture. And when public awareness is raised, policy change is implemented, governmental change is implemented, and decision makers are forced to take the correct decisions to better manage our Earth. Two examples of satellite and space systems that are currently being used and will be used in the future to monitor climate change are the Orbiting Carbon Observatory 2 and the Argos network. The OCO2, for short, will be launched by NASA to monitor carbon dioxide content in the atmosphere, and it will help scientists identify sinks and sources of carbon dioxide. The Argos network employs a series of environmental sensors all over the world. It's used ocean buoys to identify increases in oceanic temperature. This information is relayed directly to scientists through the satellite systems. It's this real-time, up-to-date information that gives scientists an idea of what is happening currently and what needs to be done now. Another more in-depth example of a current satellite system that is being used to monitor climate change is the Greenhouse Gas Observing Satellite, developed by JAXA. It uses 56,000 data observation points from around the globe to monitor current carbon dioxide density in the atmosphere. This is an improvement on the current poorly distributed terrestrial network, and it adds to the measurements from these. It's reduced uncertainties in current CO2 flux estimates by up to 40%. And it's estimated that reducing uncertainties like these will aid us in climate change prediction, and it will aid us in climate change management. So today we've talked so far about a lot of the sustainability problems that face Earth, and there's many more that we haven't mentioned. And we've also talked about some of the space and satellite systems that can be used to help us mitigate these problems. The question then remains, do we have a sustainable space for these systems to operate in? Will we have access to these systems? Well, let's take a ride up to space and invite my friend Ron up here to talk to you about some of the problems facing space, some of the problems facing these systems, and we'd like to know how we can fix them.
3, 2, econ, launch commit, go.
space after experiencing an epic ride. You can imagine. Hi, I'm Ronak Manoharan. We've seen and discussed how life and processes on Earth are driven and benefit from space-based systems. Let us now discuss how these very systems that support life on Earth are under threat. So what are some of these threats and challenges presented to these space systems? We have space weather. We have the flooding of the radio frequency spectrum. We have orbital congestion. We have orbital debris. And we have something called the lack of sufficient space situational awareness. I'm going to discuss a couple of these, and then my friend will continue on with the rest. So let's begin with space weather. Well, space weather is defined as the interaction between charged particles and radiation ejected from active regions from the sun with the Earth's magnetic field. And these are also known as geomagnetic storms. Now, these events occur during things called solar flares, which is a sudden brightening observed on the sun, which normally corresponds with a high energy burst, or events known as coronal mass ejections, which are massive bursts of energy and magnetic fields from the sun's atmosphere towards the Earth and in all directions, really. So why is it dangerous? Well, these charged particles can affect normal functioning of spacecraft or satellite. When these particles build up a surface charge, which can result to short circuits to electric components on board the spacecraft. And these can cause partial or complete failure of a satellite. And in the case of complete failure, these contribute to space debris, which will be discussed later on in the presentation. In addition, we have these very events that can damage terrestrial systems. To give you an example of damage to spacecraft, in 2003, NASA's ACE satellite experienced temporary malfunction or failure as a result of a solar storm. Fortunately, it came back online after a couple of weeks. And then in 1998, we had the Galaxy 4 satellite that failed completely as a result of such an event. An example of damage to terrestrial systems includes the 1989 event of a geomagnetic storm that caused failure to the power grids, which resulted in a large-scale blackout. So what is being done about it? Well, currently, the way we address such events ranges from limited satellite protection, like protective coverings, temporarily shutting down of systems so that short circuits can be prevented, and advanced warning monitoring systems, which uses a combination of ground-based solar observatories and solar weather satellites to forecast such events. However, such models are limited in what they can achieve, in that they can provide reasonably accurate short-term predictions. But in order to create a sustainable space future, we need models that can give us more long-term predictions, because events such as the 2003 solar flare are intense, and there are a possibility of such events of happening in the future of far more greater intensity, which do not provide us with sufficient time to react and take preventative measures. So there's a need of robust models. Moving on. Our use of near-Earth space is limited when it comes to the physical location of satellites, also referred to as orbital slots, and the radio frequency spectrum. And as society's needs, our needs, increase, such as owning more than one mobile phone, so do our reliance on satellite applications that drive these very technologies. And as a result, these resources are becoming congested because of the number of satellites that we already have up there and those that are being planned to be sent. They're being contested because you have nations vying for that spot in space to get that coverage, to get that competitive advantage. And they are competed. Once again, you have these industries trying to provide their customers with the best service for the cheapest price. So let's begin with the problem of the radio frequency spectrum. As you've already heard, and as was mentioned, many satellite applications make use of the radio frequency spectrum for applications such as telecommunication, Earth observation, position, navigation, and timing. However, the physical laws underpinning the spectrum mean that only a limited section is available for use. In addition, one of the biggest restrictions imposed on this spectrum is the Earth's atmosphere that absorbs the signals transmitted over most frequencies. So we have this issue of a limited spectrum that's useful for satellite communications, and it is debated that the US will run out of spectrum in 2013. Now we have a body known as the International Telecommunications Union, or the ITU, that allocates and coordinates the use of frequency to avoid harmful interference between different users of the spectrum. The bottom line is, unless technologies or processes are developed or invented to better manage, to efficiently use the spectrum, we face the real threat of running out of it. Moving on to orbital congestion. Orbital slots are a rare and sought-after resource, as more nations plan to gain access to space and launch satellites. Specifically, slots in geostationary and geosynchronous orbits, known as geo-orbits, located about 36,000 above the Earth's surface, and sun-synchronous polar orbits in low Earth orbit, or LEO, located about 130 and 1,000 kilometers. They serve unique purposes. For example, geo orbits are usually used, or mainly used, for telecommunication, while LEO, sun-synchronous LEO orbits are mainly used for optical remote sensing. So there are a limited number of slots available. Once again, we have the ITU that allocates slots to avoid frequency interference. And these slots are spaced between 1.5 and 5 degrees, which might not be extremely clear on this diagram. And it's done so depending on the frequency band that the satellite uses. And you might find certain slots with multiple satellites stacked up. That's because you have satellites using different frequency bands that are able to use the same slot. The problem we have here is that we have several satellites launched by different nations that perform the same tasks. And this is probably not the most efficient approach to our use of what is limited. Collaboration on satellite projects in these orbits by cooperation of different nations is one way that these nations are trying to reduce congestion and better use the frequency, the radio frequency spectrum. However, there is further need of such collaboration if we are to create a sustainable space future for the global south in terms of their access to space. However, these are not without their corresponding challenges. I would like to leave you with this video. And there's several things in this video. We have the yellow spheres that represent the satellites. Shown here are the LEO orbits, polar orbits. And we also have the white dots and the red spheres, which are space debris. And to talk about that, I would like to invite our next speaker, Greg, to explain how these pose a threat to our space-based systems.
So what the animation shows is a lot of debris and a lot of satellites out there in the various orbits. So I'm going to talk a little bit about orbital debris, also known as space debris. So what is space debris? Space debris, orbital debris, can be simply classed or defined as objects in space, man-made objects in space that no longer have a useful purpose or a function. There's three main causes to the creation of orbital debris. First of those is satellite launches. Rockets putting satellites up into space will leave behind rocket bodies, tanks, and fairings through their progression up into the various orbits. There's also explosive bolts used to separate fairings from payload and from the rocket bodies, creating more debris. Second is satellite deterioration. So we spoke a little bit earlier about solar weather. Solar weather can actually degrade and erode the surfaces of spacecraft, causing small flecks of the surface of the spacecraft to depart the spacecraft and just essentially create more debris out there. And the last one is fragmentation. So collisions between debris and satellites, and collisions between satellites themselves create vast amounts of debris. We can also have fuel tanks exploding. So discarded fuel tanks sometimes have a bit of residual fuel inside them. They can spontaneously combust, or if they're impacted by other debris, they will explode. There are also full fuel tanks up there from satellites that are non-functional or didn't make it into their assigned orbits. These also pose risks. And the last fragmentation threat is the debris caused by anti-satellite weapon testing. There's two other causes or classifications. Certain types of rocket engines or rocket motors produce very fine, very small particles, solid particles from the combustion residue. And there's vast plumes of these residues out there in the various orbits, right out to GEO. And the last one is lost and discarded equipment. Astronauts on spacewalks or extravehicular activities occasionally in the past have lost bits of equipment or simply just thrown things away. And there's also been simply rubbish just dumped overboard in the earlier days of the space race. So you can see some of the origins of a lot of the debris that's out there. In terms of sizes, they vary from microscopic, way less than 1 millimetre, up to entire satellites. The largest known satellite up there at the moment that is non-functional weighs about 8.5 tonnes, and it's in a very stable orbit, about 800 kilometres altitude, going around the poles. The polar orbits are amongst the most congested out there. So if that satellite were to be impacted by a piece of debris or another satellite, there's going to be a large explosion and creation of further clouds of debris out there. The velocities of most of the debris can be up to about 10 kilometres per second. So even very small particles have very high mass, very high energy. Small piece of debris impacting a larger object will just simply disintegrate it, just based on energies alone. Volumes, we have about 22,000 objects that we know about that are 10 centimetres or greater that are currently being tracked by the various sensors. We have another 500,000 or so in the 1 to 10 centimetre range, and it's estimated that there are tens to hundreds of millions of objects out there below 1 centimetre in size. The vast majority of those will be those combustion residue particles that I spoke about. In terms of longevity, some of these particles or objects might only last for a couple of months to a couple of years. Others can last for decades or even centuries if they're in highly stable orbits and won't return to the atmosphere for a very long time. So what are the dangers that debris poses? Well, there's a very big risk to spacecraft. So small particles can impact a component such as a solar array. The solar array might have a small hole in it. However, it may render that solar array dysfunctional. If that can't recharge the battery then runs down and the satellite will start to lose health and life and eventually will just die. That's a real risk. Components can be damaged or destroyed, and entire spacecraft can be catastrophically destroyed by impacts. There's a clear risk to astronauts up there. So astronauts on spacewalks in particular are highly vulnerable to even the smallest of particles. The spacesuit is punctured, there's a real risk of that astronaut dying very quickly if he can't get back inside the spacecraft. Also, the astronauts inside the spacecraft are as vulnerable as the spacecraft themselves to risks of collisions. One of the other threats, or one of the other dangers for us here on the surface is re-entries, or objects coming back into the atmosphere. By and by, most objects do actually burn up completely and don't make it down to the Earth. However, if they're big enough or dense enough, they can survive the re-entry process and make it down to the surface. It's shown by the couple of pictures there on the right-hand side. So we need to be able to predict where these objects are going to re-enter and where they may impact due to the threat posed to people and infrastructure on the ground. Last threat is possibly one of the biggest. It's a theory that was postulated by a NASA scientist in the late 1970s. It's known as the Kessler syndrome. And what it says, or what it proposes, is that the density of objects in the low Earth orbits, so the lowest orbits that we have, may become so great that collisions between objects or debris inside that orbit causes debris that collides with other objects. That causes a cascading effect and renders, or potentially renders, that orbit unusable or unsafe for manned spaceflight and potentially unusable for satellites. We haven't got there yet, but potentially that may not be too far away if we don't stop the creation of debris. So this quick animation, just shows the steady increase of the creation of debris from 1957, the launch of the first satellite, Sputnik 1, through to today. There's a fairly steady rise there with a sharp spike towards the end here. The spike there is caused by the only known collision of two satellites, as well as some anti-satellite testing events. So it does illustrate the vast amount of rubbish that's out there. So what's been done about it? There's mitigation methodologies are being put into place or being developed. So the idea is to reduce the creation of debris from current and future space activities, and that's going to be underpinned by developing policies and regulations. Down the road, those policies and regulations may be enacted into domestic law, and if enough nations around the world develop similar laws, then ultimately the UN can ratify those laws as international laws. Currently, the United States, so NASA, supported by the US government, is the leader at the moment in developing policies and regulations. However, the other main spacefaring nations, Russia, France, Japan, as well as the European Space Agency, are all following suit and developing their own policies and procedures or regulations. So that's a really good thing. Active removal is being used at the moment. So for objects in low Earth orbit, there is the option there to deorbit those satellites at the end of their useful life and burn them back into the atmosphere, obviously with the intent that they completely burn up. The other thing that we can do that is being used by most satellite operators today for satellites out in geosynchronous orbit, which is the one out at 36,000 kilometres. Once those satellites reach the end of their useful life, they can be pushed out another 100 to 200 kilometres, for example, into a deeper orbit, moving them away from that congested belt and placing them in an area that doesn't pose danger to other spacecraft that are still active. The problem with both of these, or the issue with both of these concepts, is that the spacecraft needs to have enough fuel remaining on board to perform those manoeuvres. This causes a cost in terms of reducing the operational life of the satellite, as well as more fuel, which means more weight, which means a more expensive launch cost. So those considerations to think about as well for satellite owners. And the last one there is man-made systems. So technologies are being conceptualised and theorised at the moment, which will in the future enable us potentially to actually go up there and use robotic spacecraft, for example, or other types of equipment to physically remove debris from the lower orbits or other orbits if they can manage to design these technologies. There's a couple of examples shown there. But as I said, they're just concepts at the moment. So the technology isn't quite there yet. So that's a short spiel on debris. We'll just talk a little bit now about space situational awareness. So what is it? It's the characterisation or the determination of the space environment and the objects that are in it, and what the effects of those two are on other space activities that we might be concerned about. It considers the positional or the orbital information of objects in space, and can also combine that with space weather to provide the broad situational awareness picture that we might need. In terms of the positional or the orbital information of objects in spacecraft, that's performed through the use of ground-based radars and telescopes. Why do we want to do this? As you can appreciate now, we have a fairly large congestion of more and more satellites being launched into orbits and the debris that is created by those events. So we need to be able to track the debris and track the satellites to know where these pieces of equipment or where these satellites are, so that we can prevent collisions, saving satellites, preventing the creation of more debris, and also safety of flight or safety of space flight for astronauts. So it's paramount that we're able to do this effectively. The two largest operators of space situational awareness sensors at the moment are the United States and Russia. Both of those systems are military-based for other purposes, but are being used now to track debris as well. Okay, the European Space Agency is currently producing or developing its own space situational awareness network, and that's currently being tested and evaluated. Might come into operation later on in the decade. There's two main non-governmental organisations that are out there as well that can contribute to space situational awareness. First one of those is the International Scientific Optical Network, or ISON. It's headed or led, if you like, by the Russian Academy of Sciences in Moscow. And it involves a number of universities around several nations with about 30-odd telescopes of different sizes, enabling them to see from the lower orbits out into deep space. So there's a lot of data that can be produced by those scientists and researchers to be shared. And the other one is the Space Data Association. This is a small collection or a small association of a handful of satellite operators who provide each other with their data about their own satellites. They don't use sensors, they just use data for location and sharing. However, the data is only shared internally amongst themselves. Which brings us quite nicely to collaboration and data sharing. So I've just mentioned 3 or 4 or 5 different operators or networks that are available out there. Some of those are quite large, some of them are a bit smaller. With the exception of the United States, most of those users do not share the data. So the US again leads the way. They share all their unclassified data with operators of satellites. It was determined by them that it was in their best interest to avoid further collisions in the various orbits, which is the reason they decided to do that. It's not so clear what Russia does with their data. The European Space Agency has declared it will be sharing their data with other agencies once their system's up and running. And ISON and SDA are the 2 other potential agencies for globally sharing data rather than amongst themselves. The other challenge we have at the moment is that, as you would have seen on the first graph, most of the sensors are in the Northern Hemisphere. What that means for us in the Global South is that we have an opportunity to contribute to sensor networks or sensor basing or whatever the case may be to assist in generating more situational awareness data. So what I've just seen there on the animation is the use, or in this case a lack of the use, of space situational awareness data. The yellow satellite was a non-operating Russian satellite which was determined to be on a collision course or potential collision course with the blue satellite, which is one of the Iridium constellation. Information was provided to the Iridium company. The decision was taken based on the very, very low probability of intercept or of a collision to actually not manoeuvre their satellite in this case. So satellite manoeuvres do actually occur on a fairly regular basis by satellite owners. In this case, they made the decision not to, and unfortunately that was the result. 2 large clouds of debris being produced and just adding to the waste that is out there. So you've heard a number of issues from Earth sustainability and space sustainability. What we'll do now is discuss some of the links between both of those. So I'll hand over to John and Long to take you through that.
All right, cool. Thank you very much, Greg. Let's get into the crux of the problem and emphasise the Earth-space link. My name is John Finesse, and I'm from Adelaide, Australia. And
my name is Zhang Long, come from China. Good morning.
Okay. The space-Earth relationship is mutually beneficial. We depend on satellite applications, and satellite applications are at risk. So, space sustainability is an Earth problem. In this section, I will talk about the fundamental role of satellite applications. Long will then talk about our global economic reliance on the systems and some unique applications in the Global South that we are dependent on. I will then conclude by talking about public awareness and education. So, what is the fundamental role of satellite applications? It's about learning and understanding the Earth, a process we've outlined as photons to electrons to neurons to actions. Let me go into some more detail. Satellites are orbiting the Earth. They collect photons or light particles by their sensors. This is then converted into an electrical signal consisting of electrons, and it's then interpreted by our brains, the neurons. We can then act upon this information. But there's something so important in between, something a little bit abstract, but something that we've termed knowledge acquisition. It's the point in the satellite data information process at which the end user understands the provided information and can take action thereupon. It's about understanding the information and applying it. It's about building a knowledge base, knowledge that we can use, knowledge that can help people, and knowledge that can save lives. Okay. The UN Millennium Goals were developed in the year 2000 following the Millennium Summit. They established 8 international goals. And we believe that satellite technologies play a fundamental part in achieving these goals. We could eradicate poverty and hunger. We could achieve universal primary education. One moment. We could promote gender equality and empower women. We could reduce child mortality, improve maternal health, combat diseases such as HIV, AIDS and malaria, among other diseases, ensure environmental sustainability, and establish a global partnership for development. We believe that satellite applications can help us achieve these goals. But we also rely on satellite applications in our daily lives. I'll now pass it on to Long, who will talk about our global economic dependence and some unique applications of satellite technologies in the Global South.
Thanks, John. Space technology can help us, you and me, develop and improve our lives. Next, let's look at space technology applications in the Northern and the Southern Hemisphere. Satellite technology makes a major role in the economy of developed nations in Northern Hemisphere. In Europe, between 6 and 7% of GDP relies on PNT, position, navigation, and timing space technologies. The European Union has developed its global navigation satellite system, Galileo. It is anticipated that Galileo will generate between 60 and 90 billion euros in economic and social benefits. In America, the mine industry sector relied on PNT technologies, including delivery services, banking, agriculture, and communications. Altogether, these sectors contributed an estimated 9.5% of United States GDP. That's over 1.3 trillion United States dollars. Let's turn to Southern Hemisphere. In the Global South, we can see many examples of Earth and space relationship. In Southern Hemisphere has its own specific problems in space technology applications. Growing population, increasing bandwidth demand, unique applications of space technologies, and the low population Johnson. In the Southern Hemisphere, people rely on this space technology in their daily life. In Africa, with the population growing, the requirements of the combination makes increasingly more and more. 80% of internet and 60% of 500 million cell phones in Africa depend on satellite. In Southern America, Brazil increasing autonomy by developing its domestic satellite system. Society around the globe has become increasingly dependent on satellite services. Joe.
Thank you very much, Lon. So now we understand this global economic dependence and some of those unique space applications. But are we truly aware of these? And that brings me to public awareness and education. So when I say space, what comes to mind? People often think about the Apollo missions, going to the moon, the space shuttle, and riding a rocket into space. We are all too familiar with the romance and heroism of human space exploration. but that's blanketed our understanding of the true benefits of these space technologies. It is paramount that we understand the utilitarian and humanitarian value of these benefits, and we instill this into our culture. Despite using satellite applications, as satellites fly high up in the sky, they go unseen and their importance goes unrecognised. So within this next slide, we saw this image earlier, or at least from another perspective. I'm sure it's an image you've seen before, or something like it in the news or maybe in the weather. You are familiar with these images that come from satellite applications. But is the general public, or are you, familiar with the risks? In the World Economic Forum survey of global risk scales, the proliferation of space debris, amongst many other risks, was rated to have a very low impact on society. And this is within the section of technological risks. But if you consider the economic risks, the environmental risks, the geopolitical risks, and the societal nature risks, proliferation of space debris appears right in the bottom left-hand corner here of a scale of likelihood and impact. We're not aware of this risk. People do not understand it. But the thing is, subject matter experts rated this risk much higher than other survey participants. And this suggests that education may be the key in raising awareness of these issues. So let's bring space back down to Earth and into the classroom. We can use science, technology, engineering and mathematics education, or STEM subjects, to help raise awareness. Space agencies such as NASA, the European Space Agency, the Canadian Space Agency, the Indian Space Research Organisation, all use educational media to bring the message across. In the Global South, we have the Victorian Space Science Education Centre, which runs programs for those ages 10 to 15 and professional development learning programs for teachers. In Nigeria, they have the Junior Engineers, Technicians and Scientists program, which is a government initiative fostering excitement and enthusiasm for space technologies, where students work for a week to prepare an exhibition of a science experiment. They really get excited about space and science beyond the schoolyard. But not only can we use... Not only can we use STEM education to engage public interest, we can also use it to foster a new generation of engineers, scientists and technicians, even space lawyers, that understand the importance of these applications, that realise that we're dependent on these technologies, but they're also at risk. And they can work collaboratively, maybe internationally, together to fix this problem. The space-Earth relationship is a symbiosis, a strong, intimate bond, which we've symbolised here with this heart, as you can see, if it wasn't obvious. It is so essential, from what you've been learning today, that we maintain and ensure that the space environment is there for future generations. Thank you. On to Will.
Oh, cheers. Thank you, John and Long. My name is Will Reid, and I'm going to be talking about some of the recommendations that the Common Horizons team has come up with. Before I start, I'd like to bring you back to our mission statement. Our mission statement is to recommend space sustainability solutions to the Global South for the benefit of Earth and all humankind. Now, to recap on what my colleagues have been discussing, our use of space is critical for life here on Earth. Our societies have become dependent on telecommunications, position, navigation and timing, and Earth observation satellites. But this is under threat. This infrastructure, this critical infrastructure, is under threat from orbital debris and the flooding of the electromagnetic spectrum. So we have to sit down and ask ourselves some questions. Some very difficult questions. The people that you see behind me have spent the last 5 weeks sitting down and discussing some questions like, what is the nature of the problems that we have to address? What is the nature of orbital debris? What is the nature of the flooding of the electromagnetic spectrum? How can we better understand these problems? Then, what can the Global South do to solve these problems, to help the situation? But most importantly, what can we do to bring about change? What can I do? What can you do? What can society do as a whole to bring about change? Because if it isn't already evident, change is necessary to solve these problems. So, the recommendations that we have come up with look at 3 main themes, a 3-pronged attack, if you will. We look at policy, awareness, and technical solutions. First off, I'd like to look at policy. The building that you see in front of you is a United Nations building in Vienna, and it is home to the UN COPUOS, or the United Nations Committee for the Peaceful Uses of Outer Space. They like their acronyms at the United Nations. The UN COPUOS has come up with effective policy to address space sustainability problems, especially the prevention of added space debris. Similar committees such as the IADC, or the Interagency Debris Coordination Committee, have also come up with policies that address these issues. We have the ITU, or the International Telecommunications Union, that Ron spoke about. And this union allocates frequency bands, which can be used by geostationary and geosynchronous orbital satellites especially. Now, these unions, committees, they exist. They have existing policies. It is our recommendation that the Global South embrace these policies. The Global South is currently highly fragmented. The Global South needs to come together, look at these policies, and adhere to them. Next, I'd like to talk about awareness. John touched on this topic and how important it is to make the individual aware of these problems. For without the individual knowing about these problems, we ultimately get nowhere. So our recommendation is simple: spread the word. Like policy, there are existing awareness campaigns that happen all year round. Yuri's Night is a fantastic example. Every April 12th, a whole bunch of people around the world get together at parties and talk about space. They get together on April 12th because they're commemorating Yuri Gagarin's flight into outer space, the first man to orbit the Earth. They also like to drink a little bit of vodka as well. The World Space Week is a United Nations initiative that's focused particularly on the classrooms. It focuses on inspiring teachers and inspiring schools to use space to conduct STEM educational activities, focusing on science, technology, engineering, and maths. Space can be used to inspire people. I'm sure all of you in this room have at one stage been inspired by watching the space shuttle launch, watching men walk on the moon, watching Curiosity being lowered onto the surface of Mars. Space can inspire. We also propose that new social media campaigns be implemented, such as the Day Without Space skit that you saw at the beginning of this presentation. They're fantastic ways of bringing the message of space sustainability and the link between Earth and space. I think we intend to film that and put it online. Hopefully it'll go viral. We also would like to promote the use of educational workshops. We have to educate our politicians, our lawyers, our engineers, our scientists, and especially our teachers in these problems. And what can be done about these problems? The people that you see behind me, they've just been doing a 5-week intensive educational workshop. It's programs like these that need to be used globally to address these problems. I'd also like to highlight a innovative little tool that one of our team members, Scott Dorrington, has produced. He has proposed the use of a doodle on a particular search engine that rhymes with Oogle and starts with G to highlight the problem of space debris. He has actually written to Google. Oh, I said it. He's actually written to the search engine and proposed that they make one of their nice little doodles that the user can interactively play with and see how our near-Earth environment has become populated by orbital debris. So we've covered awareness and policy. Now I'd like to get on to what we can do to really address these problems, which come in the form of technical solutions. As an engineer, technical solutions, oh, I like these. They're fantastic. But one of the most difficult things to do is sit down and say, hey, how do we create these solutions to big problems? How do we design these solutions? And this is a difficult process. I'd like to bring you to how the United States put men on the moon. First off, you had inspiration. You had an inspirational figure in the form of JFK, standing at his podium saying, we will send men to the moon at the end of this decade. Big inspiration. They had a lot of money, billions of dollars invested in this program. Competition in the form of the Soviet Union. A management structure in the form of NASA, and ultimately experts, scientists and engineers that actually implemented these systems. But unfortunately, this model was unsustainable. The last moon mission, well, manned moon mission, was in 1972. We propose that to create sustainable solutions, that we follow an incentive-based prize model. Some examples of this incentive-based prize model come from the Orteig Prize and the X Prize. The Orteig Prize was offered to aviation enthusiasts in the 1920s, and it was a $25,000 prize that would be given to the first team that could fly from New York to Paris. In 1927, Charles Lindbergh, on board his Spirit of St. Louis, won this prize, and this event has been widely considered to have had an extraordinary impact on the development of the aviation industry. The X Prize, a bit more recent. The ISU co-founder, Peter Diamandis, set up this X Prize Foundation, which offered $10 million to the first team that could launch the equivalent of 3 human beings into a suborbital space flight twice in 2 weeks. A big challenge. Companies throughout the world put up proposals, and one company in particular, led by Burt Rutan, launched the Spaceship One in 2004, and they won the $10 million, and now the space tourism industry is still in its infancy, but it's coming into reality. 20 years ago, it was part of science fiction. So, to address the technical solutions for orbital debris, electromagnetic spectrum flooding, we propose what we like to call the S Prize, a Global South Space and Earth Sustainability Prize Foundation. Now, imagine a prize that would offer $10 million for the first team that could successfully deorbit 2 spent third stages that are stuck in orbit. We propose that this foundation is set up to bring together existing global south space industry, global south government, investors, entrepreneurs, bring them together and form this foundation so that they can efficiently and sustainably invest in their future. If we've learnt anything today, it's the collaboration between all these parties that will create real solutions. So I'd like to bring you back to our 3 themes: policy, awareness, and technical solutions. It is only through these 3 things that we can accomplish, that we can solve these major challenges of our time. To borrow a couple of words from JFK, we do these things not because they are easy, but because they are hard. I would like to draw your attention to our website, commonhorizons.wordpress.com, where you can find our white paper and an executive summary of our white paper online. We also have the white paper up there in Chinese to emphasize our international flavor. So thank you very much for your attention today, and I'd like to get Alejandro up here to answer your questions.
Not really.
Sorry?
I'm answering the questions.
Yeah, you're answering the questions.
Hello, thank you. We are now open to questions. Please raise your hand if you have one. And since I have a microphone, I will repeat them to make sure that they are well understood and our team can successfully answer them. Yes, please.
So you've outlined that satellite applications such as Earth observation, remote sensing, and position navigation timing are definitely capable of benefiting humankind, especially those who are detached from urbanisation. But in what way could satellite applications encourage or assist those of us who are living in the developed world, so those of us who have access to smartphones and are aware that there is climate change and that the Earth is in decline? How could these applications encourage us to live more sustainably?
Yeah. So the question was, how can satellite applications help us, well, the people living in the developed world, and how can they help us live more sustainably? You want to answer that one? Scott?
So satellite applications, as you saw at the start of our presentation, are already a cohesive part of the developed world. They're used for, GPS is a great example of where satellite application is used throughout cities and terrestrial urban infrastructure. Remote sensing is also a really powerful tool for people who live in cities. You have your weather satellites, which form a strong part of your daily forecast. You have satellites which monitor climate change, like the Japanese GOSAT. You have
countless satellites which address numerous problems. And they're also critically important in disaster management. If you live in a terrestrial town and there's an earthquake or a flood, as happens in Queensland, and your terrestrial communications network is damaged, there's no way you could, it takes time and effort in order to fix the problem. Satellite applications, satellite communications can easily be rolled in using very small aperture terminals in order to facilitate communication and re-establish them in a short amount of time, which is critical in disaster management.
Thanks. I think Miguel wanted to add something to this.
Good morning, I'm Miguel from Brazil. I am living in Global South because Brazil, South American country. I can say with property that satellite application can be very suitable to our sustainability. Brazil has a very large area of a very big rainforest that is responsible for climate change in Brazil and other areas around. And INPE, our Institute for Space Research, develops programs develops satellites and launchers to help us to understand and monitor the effects on the forest and the rivers and all the climates in Brazil. Also, the satellites in our space programs are used to reach the geostationary orbit in order to provide internet data connection to our isolated and far communities in the rainforest and outbacks and poor region that the state cannot be effectively present. And then we can use the remote sensing for improve our life and climate change. Also, we have developing now a Center for Disasters Forecasts, which will help the people that live in south of Brazil to be safe from floods and storms, rains that kills people every year on that region. Also, I can say that satellites, communication satellites, could be used to improve the education and health in Brazil and outback areas that are very hard place to live, very far, very drought, and we cannot we can reach a low cost access to education than to university, giving us the internet and data connection. Thank you.
Thank you, Scott and Miguel. Any other questions? Yes, please.
Hi. Thanks, guys. It was a great presentation. One thing that I thought perhaps you might touch on, and I don't know if you considered this in your report, but I'd like to know if you did. In terms of considering using space for sustainability in the Southern Hemisphere, one of the very key issues I would have thought is how do you actually access that space data into the future? Because most of the countries in the Southern Hemisphere are not in a position to be able to provide all of that data themselves with their own satellites. For example, Australia doesn't have a single Earth observation satellite of its own at all. And you did mention the disaster charter. We know that we can get access to satellite imagery in case of disasters. But what about access to all of the other useful space information that you mentioned that all of these sustainability issues rely on? Did you consider how you would actually assure the access of these countries to that data?
Thank you very much for the question. So I believe it was how would the countries of the Southern Hemisphere, especially the ones which do not have their own satellites, how can they ensure access to the data that is required for these applications that we have just talked about?
Yeah,
Chris, please.
Start with an answer for that. One of the ways that Australia itself is planning to continue to ensure access to this data is through policy. And because policy is one of the things that guides what a country does and how it goes about its business. And so later on this year, very soon, as a lot of you are probably aware, we're expecting our first we've had our principles for essentially a space policy, and our first space policy, and later on this year the satellite utilisation policy will be coming out. And what the principles for the space policy essentially say is that among focusing on the three main applications, because those are the things that Australia uses the most and has the most direct benefit from, one of the things that we will focus on with this space policy is to ensure access to these data systems through collaboration. And part of that involves investment in getting the data, and so we contribute to systems that other countries put up. And I think it's about $100 million a year Australia will spend on satellite data and gaining that from other countries. So for small contributions, we are able to gain access to this data, and the contributions are actually very small in comparison to the costs of sending up the overall systems. So we can contribute in small amounts to those, and what we gain back is the data. And that's why the focus is put so strongly on collaboration. And as a global south, that's why we can get so far with our collaboration.
Thank you, Chris. Miguel, would you like to make some additions to this?
I would like to make another compliment to the speech of our colleague. Brazil, our Institute of Space Research has a program to share the data from remote sensing of our satellites that can be freely accessed to all countries to use for their sustainable management and all the other uses. Then I think that we can use the partnership to share, as Australia is doing, information for other countries, and then we create a good scenario for sustainability for all global south.
Thanks, Miguel. Any other questions? Yes, please.
Thank you for your presentation. It was a wonderfully professional job that you did and very thought-provoking. I have an interest in space debris, and I wondered whether someone could tell me very briefly just a little bit about how difficult it is to remove it. And I guess I get that, but whether there are any current ideas about how we might do that. And one suggestion, or a slightly left field idea that you might think about, if you walk outside anywhere in South Australia, you won't see a bottle or a can or a cup, which is quite unique in Australia. And the reason you won't see them is that we put a little levy on the people who create the debris in the first place, and then that levy becomes an incentive for other people normally, to pick it up and take it back. And so I wondered whether you had thought about applying the same principle.
Yeah, I believe the question was on space debris and why or how it's difficult to remove it, and also if there are any proposed ideas on how to do this, and how to tackle debris mitigation and not the idea of not creating more debris as well as actively removing it. Please,
one of the things we did sort of suggest or discuss amongst ourselves as a possible recommendation, but we didn't actually use it in the end, was the concept of, as you said, an incentive type program or process where launch agencies or nations might be encouraged to somehow receive a benefit or receive a benefit back to them that they might invest if they can successfully deorbit a satellite, for example, or push one out into deep orbit. We didn't really go into too much depth in that because we decided to focus on some other areas. I think your initial question regarded some current technologies or emerging technologies. There's one out there which involves using lasers, high-powered lasers to, well, the theory anyway is to try to, as probably aware, try to push or ablate some of those debris items up there, just bump them off their orbit very gently and induce an oscillation in their orbit which might result in those being naturally decaying into orbit by themselves. That's fine in itself, but it brings about some other questions in relation to civilian use versus militarisation of the laser. So if the laser can be used to remove debris, then potentially it has military application as well. So there's some policy and legal questions to be answered down the road with concepts such as that.
Thank you, Greg. Any other questions? Yes, please.
I'm interested in your idea of sustainability. So for our planet, our system, I believe that it's not just human sustainability, but the sustainability of the whole system, plants, animals, ecosystems and so on. So can your group provide me evidence of the fact that if we use more technology, more space systems, that in fact we won't contribute to less sustainability of the total system?
Okay. So the question was that we have explained how our satellite technology can provide sustainability from the human perspective, but how can we ensure that this sustainability does not have negative effects in the sustainability of the whole Earth and the whole biosphere on Earth?
With regards to sustainability of the entire Earth, precluding the human segment, there are a number of initiatives which have already been taken into account. Two things I want to touch on. One is the concept of green space, which is where launch organisations and other companies use green technology which benefits Earth, so non-toxic rocket fuel, which has water vapour instead of aluminium particulates as their exhaust plumes. That contribute to a more sustainable Earth. And this includes also the large infrastructure requirements to build a satellite to manage the program, which you see across all manufacturing and all corporate investments these days. The second thing I want to touch on is there are satellite programs out there which are used exclusively, or not necessarily exclusively, but are used for conservation, as was mentioned with the rainforests in Brazil. Also the Argos network that we mentioned, which monitors sea level temperature and several other things, is used for tracking animal wildlife relocations throughout their life. So you put a little transceiver on them and you can track their migration paths and you can monitor how many animals are left in a population, if they're undergoing severe types of forms of strain in their daily commutes or their annual relocations and migrations, and you can see what is at risk. That's the primary purpose of Earth observation networks for sustainable Earth. You can see what is at risk, not just in the human context with your urbanisation and your slums and your agriculture, but you can see what is at risk in your environmental context with greenhouse gases, animal tracking, and everything that comes along with that.
Okay, thank you, Scott, and thank you very much for your questions. I would now like to make some final remarks to emphasize some of the points we made, and some of you might recognize the speech these are inspired on. So, as we have seen, the hazards of outer space are hostile to all of us. Its responsible use deserves the best of all humankind, and its opportunity for peaceful cooperation must be continued to be exploited. But why, you may ask? Why make a sustainable use of outer space? Why make this our goal? But you may well ask, why recycle? Why tackle climate change? Why care about those people for which hunger forms a part of everyday life? And why? Why did we spend uncountable sleepless nights in working on this project? We believe that this will lead to a better world. A world in which goodwill international collaboration will be taken for granted, and human suffering will be reduced to a minimum. This is a challenge that we are unwilling to ignore, and one we can't afford to postpone. Finally, one which we intend to overcome. It is for these reasons that making the recommendations explained today is one of the best and most important decisions that we will make throughout our careers. Let's share common horizons. Thank you. I would like like to thank you, we would like to thank you all for attending our presentation and listening to our ideas. We would also like to thank our staff for leading us to this incredible journey. UNESA for the invaluable contribution to organizing and hosting this program. A special thanks to our technical team, which without them we wouldn't have been able to present today. And finally, to all our ISU family, thank you.